Hello, welcome again to the third part of our lecture entitled More on Triple Integrals in Rectangular Coordinates. Remember from the second part of our lecture that we were talking about this example, and we were treating the solid as a solid of type xz. And then we said before that there's a problem if you force yourself to treat this as a solid of type xy because at some points the ceiling is the blue surface and at some points the ceiling is the pink surface. So now, because really projections onto the xy plane or treating solids as an xy as a solid of type xy, it's a very natural thing because you always want to project to the ground, right? So let's force ourselves to treat this as a solid of type xy. Okay. So the compromise here is that because the ceiling functions are different, we have to divide the region into two in such that in both regions the ceiling functions would be will be uniform. So this is the rectangular projection onto the xy plane, and you have this line that divides those points where on this region, on this sub-region, the ceiling would be the pink surface, and on this sub-region, the ceiling would be the blue surface. So this is in fact this line here, okay? And how do you get the equation of that line? Because that will be important later when we will be getting the limits of integration of the double integral, no? So yung outermost integral, no, which is the double integral. So now we find the equation of this line, and remember that this line here, it is just the projection of this line. So maybe we find the equation of this line and then try to project it onto the xy plane. So how do you get the line of intersection? So here we have a plane of intersection. This is a typo. This must be a line of intersection. So how do you get the equation, the line of intersection of two planes? So I think you've done this before in Math 22. I hope you still remember it. But what is very easy is that because you want an equation on the xy plane, you try to eliminate the z's. So here, let's do this by elimination or substitution. So let's isolate z from the first equation and then substitute it into the second equation. So z here is 2 minus 2x. So instead of writing y plus 2z, we write y plus 2 times 2 minus 2x equals 4. And then solving that, we get y equals 4x. Now, I hope you are not confused that we got a y equals 4x as the equation of the line. In fact, y equals 4x is not the equation of this line because y equals 4x is an equation of a plane. The lines in 3D, remember, are parametric equations, or you can also write them as symmetric equations. So in fact, you still have to write here 4x equals, so you have y equals 4x equals, so you see here that y is equal to 4 minus 2z. So you have this y equals 4 minus 2z. So this is the symmetric equation of the line of intersection of the blue and the pink surface. But because we're just projecting it onto the xy plane, we ignore this part here where you equate it with a function of z, and we just look at y equals 4x. So here, indeed, the equation of this line is y equals 4x, and this is the projection again of this line of intersection of the two surfaces, the blue and the pink surfaces. So we write G, the solid, as the union, the disjoint union of the solid whose ceiling function is the blue surface, and G2, which is the subsolid whose ceiling is the pink surface. Okay, so we remember that this was the integral to be evaluated, and then because of a property of triple integrals, we can rewrite this as a sum of triple integrals over the subdivided solids. So now G1 and G2 are full-fledged solids of type XY, and I said that because on G1 and G2, the ceiling functions are uniform. Okay, So here we have R1, no? R1 is this region here. And then you see if I uh, draw an elevation line here, the floor function will be z equals 0, which is the xy plane, so that's why you have a 0. And then the ceiling function will be this blue surface, which is z equals 2 minus 2x. That's why the upper limit of integration is z equals 2 minus 2x. On the other hand, for the subsolid G2, the ceiling function is from this equation where if you isolate Z, you will get Z equals, I hope you can do this mentally, you have 4 minus Y over 2. So that's why in the innermost integral here, you have 0 for the lower limit of integration because the floor function remains to be the xy plane, which has equation z equals 0, and the ceiling function is z equals 4 minus y all over 2. Okay? And then again, after getting the limits of integration of the innermost integral, the next problem is to also write the limits of integration of the double integral, and you can do that by looking at your projection. So over R1, so you treat this as a type 1 region. Type 1 means that you look at the vertical strip and look at the bottom and top functions. So the bottom function is clearly y equals 0, which is the x-axis, and the top function is y equals 4x. That's why you have 0 and 4x as the limits of the second innermost integral, and x here ranges from 0 to 1, so that's clear. And on this pink region, you look at the vertical strip again, the bottom function is y equals 4 minus y equals 4x, and the top function is this horizontal line y equals 4, so that you have y equals 4x as the bottom, and the top function is y equals 4. Again, x here ranges from 0 to 1. Okay, so you have these iterated integrals, and I think this is the most important step here because the next steps will just be routine, you know. So here they evaluated, so the one who made the slide evaluated double integrals in a separate regions. So you have I think this is clear. It's very easy to do. So integral of 1 with respect to z will be z, and then you evaluate it from 0 to 2 minus 2x. So I don't want to bore you with those details. So suffice it to say that the first integral will give you 4/3, as well as the second integral will also give you the same value. And because of additivity, just get the sum of these, and you still get the sum 8/3. Okay. Before we go to the second example, let's go back to the problem and see if we can rewrite this as a solid of type YZ, right? So is this a solid of type YZ? So how can you tell? So again, you have two questions. The first one is that can you define the the region the region that is a projection of the solid onto the YZ plane? So the YZ plane is this plane, right? Right? So the projection would be this triangle, sure, yes. And if you look at this, now can you define the floor and the ceiling functions? And the answer is again yes. So here you have x equals 0, and here you have x equals 2 minus z all over. So yes, so I think it's a good exercise to also view this as a solid of type YZ and see that if you do the computations, you still get the same answer, 8/3. Okay, so for the next part of our lecture, we will try to do another example.